This is the math department at Amjad High School for grade 11 complex number. This is session 3. In this session, the objectives are: first, we do a revision for the previous session, correction of the homework given in session 2. We will talk about the properties of the conjugate of a complex number. We will use the calculator Casio class with in complex mode to do calculation with calculator. We will talk about real and pure imaginary complex number. We will do some applications. Revision previous session, correction of homework given in session 2. Exercise 1. Consider the complex numbers z1 equal 2 plus 3i and z2 equal 1 minus i. Write in algebraic form the complex numbers z1 bar and z2 bar. z1 bar is the conjugate of 2 plus 3i, so it's equal to 2 minus 3i. I keep the real part and I change the sign of the imaginary part. And z bar 2, z2 bar is equal to 1 plus i. Write in algebraic form the complex number z1 plus z2 bar and z1 bar plus z2 bar. What do you notice? We have z1 plus z2 equal the sum of the two complex numbers. This is z1 and this is z2. So it's equal, I add the real parts, 2 plus 1 is equal to 3, and 3i plus minus I, so it's equal to 2i. So z1 plus z2 conjugate of the sum is equal to 3 minus 2i. And z1 bar plus z2 bar equal. z1 bar is equal, here we have it, 2 minus 3i, plus z2 bar is equal to 1 plus I. So it's equal to 2 plus 1 is 3, minus 3i plus I is equal to minus 2i. We notice that z1 plus z2 bar is equal to z1 bar plus z2 bar. So the conjugate of a sum is equal to the sum of the conjugates. We have z1 equal 2 plus 3i, z1 bar is equal to minus 3i. This is a given from the last page, last slide. Show that z1 minus z2 bar is equal to z1 bar minus z2 bar. We have z1 minus z2 equal 2 plus 3i minus 1 minus i. It's equal 2 minus 1 real part minus real part, so is equal to 1. 3i minus minus I is equal 3i plus I is equal to 4i. So z1 minus z2 bar is equal 1 minus 4i. And z1 bar minus z2 bar equal 2 minus 3i minus 1 plus I, and is equal to 1 minus 4i. We can see that they are equal, so z1 minus z2 bar is equal to z1 bar minus z2 bar. So the conjugate of a difference is equal to the difference of the conjugates. We remember here the given from previous slides. Shows that z1 times z2 bar is equal to z1 bar times z2 bar. We have z1 times z2 equal, we multiply, so here we have to do we have to expand the factors. 2 times 1 is equal to 2, 2 times minus I is equal minus 2i, 3i times 1 is equal to 3i, and 3i times minus I is equal minus 3i squared, and I squared, remember that I squared equal minus 1, so the final answer is plus 3. 2 plus 3 equal 5, minus 2i plus 3i is equal plus I. So z1 times z2 bar equal 5 minus I, the conjugate of the answer here, 5 minus I. Let us now calculate z1 bar times z2 bar. So this one is z1 bar times z2 bar is equal to 2 times 1 is 2, 2 times I to I, minus 3I times 1 minus 3I, minus 3I times I is equal to plus 3. So, and finally we have 5 minus I, and we can check that they are equal. We notice that the conjugate of a product is equal to the product of the conjugates. Now we have to show that z1 over z2 all bar is equal to z1 bar over z2 bar. We have z1 over z2 equal 2 plus 3I over 1 minus I. Remember in session 2 we learn how to do the quotient of two complex numbers. So is equal, we have to multiply by the conjugate of the denominator, which is 1 plus I. And here we have z bar is equal to real part squared plus imaginary part squared, so 1 plus 1. And in the numerator we have to multiply each term by the other. 2 times 1, 2, 2I, 3I times 1 is 3I, 3I times I, 3I squared, and is equal minus 3. And finally 2 plus 3 is minus 1, minus 1 over 2, plus 5I over 2. So z1 over z2 bar is equal conjugate of the answer here, it's minus half minus I 5 over 2. And now we have to do z1 bar over z2 bar. z1 bar is 2 minus 3I over z2 bar 1 plus I. Multiply by the conjugate 1 minus I, and is equal 1 plus 1 in the denominator, and we do the multiplication here, and finally the answer will be minus half minus 5 over 2I, which is equal to this one. So we notice that z1 over z2, the quotient, the conjugate of the quotient is equal to the quotient of conjugates. Exercise 2. Consider the complex number z1 equal minus 3 plus 4I. Write in algebraic form the complex number z bar. Very easy, minus 3 minus 4I. Show that z bar bar is equal to z. Z bar is minus 3 minus 3I. Z bar bar, we have to do the conjugate of this one. So it's equal to minus 3 plus 4I, which is equal to z, the initial value here. So z bar bar is equal to z. Calculate z plus z bar and deduce its relation with the real part of z. Z plus z bar is equal to, we have to add this one and this one. Okay, you can check here, 4I minus 4I can be simplified. Minus 3 and minus 3 is equal to minus 6, which is equal to into minus 3. Minus 3 is the real part of z. So finally, z plus z bar is equal to 2 into a real part of z. This is a rule. Calculate z minus z bar and deduce its relation with the imaginary part of z. Z minus z bar is equal, we put z here, minus z bar. Minus 3 plus 3 can be simplified. 4I plus 4I is equal to 8I, which is equal to 2I times 4. 2I times 4 is the imaginary part of z. So finally we get the rule, z minus z bar is equal to I imaginary of z. Example 3. Write in algebraic form the following complex numbers. Z equal 1 plus I over 1 minus I. We have to multiply by the conjugate of 1 minus I, which is 1 plus I. We have to multiply the numerator and the denominator to get 1. We don't have to change the. So as we say, we don't have to change the value of z. So we multiply by 1 plus I over 1 minus I. Now it's equal z bar in the denominator, so real part squared plus imaginary part squared, which is 1 plus 1. In the numerator, 1 times 1 is equal to 1, 1 plus I times 1 is equal to I, and I squared is equal minus 1. So we simplify 1 and 1, 2I over 2, which is equal to I, pure imaginary complex number. Z equal x plus iy plus 4 over x plus iy minus 3, where x and y are real numbers. First we group the real part and the imaginary part in the numerator and in the denominator. After that we multiply by the conjugate of the denominator, which is x minus 3 minus iy in the numerator and the denominator. So now we have a real part squared plus imaginary part squared. So x minus 3 squared plus imaginary part squared y squared. In the numerator we have to multiply each term by these terms. So x times x squared, x times minus 3x minus I xy plus 4x minus 12 minus I minus 4 iy plus I xy minus 3 iy, and finally minus I squared y, but remember that I squared equal minus 1, so the final answer will be y squared. Now group the real part together. We have x squared plus y squared plus minus 3x plus 4x is equal to x, and minus 12 in the real part over the denominator, plus I. In the imaginary part we have minus ix and plus ix. You can simplify. We have minus 3 iy and minus 4 iy, which is equal minus 7 iy. We put I here, so minus 7y over the denominator. This one is the real part of z, and this one is the imaginary part of z. Properties of a conjugate of a complex number. Consider the two complex numbers z1 and z2. We have z1 plus z2, conjugate of the sum is equal to the sum of conjugates. The conjugate of a difference is equal to the difference of conjugates. The conjugate of a product is equal to the product of conjugates. And finally, z1 over z2 bar is equal z1 bar over z2 bar, where remember that z2 must be not equal to 0. Zn bar is equal to z bar power n. Also, for all complex number we have z bar bar, conjugate of the conjugate is equal to z. Z plus z bar is equal to real z, as we see in the example. Z minus z bar is equal to I imaginary of z. Z bar, the important rule, z bar is equal to real z squared plus imaginary z squared. Application: given the complex number z equal a plus ib, where a and b are real numbers, this is the algebraic form of a complex number. Complete in terms of a and b the following: z bar equal a minus ib. Z bar bar is equal a equal to z equal a plus ib, because we have to change twice the sign of the imaginary part, so we'll get z. Z plus z bar is equal to real z by the rule here, and the real z is equal to a, so the final answer is 2a. Z minus z bar is equal to I imaginary of z, so is equal to ib. Z times z bar is equal real z squared plus imaginary z squared is equal a squared plus b squared. Using calculator, Casio class with in complex mode. So this is the Casio class with calculator. Go to menu to get complex. Here you can see the letter I, so we work in complex mode now. Okay, we can do whatever we want as a calculation. It's very easy. For example, 2 plus 3, when I want to put I, it's simply I have to put eng here, without shift, without anything. For example, bracket minus 6 plus 5i. Close the bracket, equal. Here is the answer. For example, if I want to put 1 plus I over 1 minus I, we see that in the example, just put equal, we get I. We see that in the slide before. Okay. We follow these steps. First step, press menu setup button. The second step, press the number 2 to get the complex mode. Third step, we can get the imaginary number I by pressing the button eng. Example, using the calculator, write in algebraic form the complex number z equal 1 minus 2i power 17. Let us do it. To do that, it's very easy. Bracket 1 minus 2i power, this one is the power 17, and we put equal. This is the answer. Okay, so the answer is this one. Now, a real and pure imaginary complex number application. Consider the complex number z. We have z is real if and only if its imaginary part is equal to 0. Z is pure imaginary if and only if real z equal to 0 and imaginary z not equal to 0. Be careful, this condition is very important, because if imaginary of z equal to 0 and real z is equal to 0, in this case z will be equal 0 plus I 0, and it will be equal to 0, and the number 0, we know that it's a real number and not pure imaginary complex number. So imaginary of z must be not equal to 0. Example, z equal 1 plus I squared. Let us do the calculation. 1 plus 2i minus 1, a plus a squared plus 2ab plus b squared. Simplify 1 and 1 is equal to 2i, and this one is a pure imaginary complex number because the real part is equal to 0 and the imaginary part is 2 not equal to 0. So z bar in this case is equal to minus 2i. And if the complex number is a pure imaginary complex number, in this case the conjugate of this complex number is equal to its opposite. Z equal 1 plus I radical 3 power 3. First we decompose the power 3 to power 2 and power 1. We start by developing this expression here. It's in the form a squared minus 2ab plus b squared, and b squared is minus 3. And now we multiply. We can simply reduce 1 and minus 3 to get minus 2 minus 2i radical 3 times 1 minus I radical 3. And finally we multiply each term, okay, to get this expression. And finally we simplify 2i radical 3 and minus 2i radical 3 to get minus 8. So z is real because the imaginary part is 0. Z equal minus 8 plus 0i if we want. In this case, notice that z bar is equal minus 8. So if z is the real number, its conjugate it's equal to its value. So z bar is equal to z if z is the real number. Remarks. A complex number z is real if z bar equals z. A non-complex number is pure imaginary if z bar equal minus z. Application 1. Which of the following complex number are real and which are pure imaginary? Z equals 3 plus 3 minus 2i into 2 minus I minus 4 plus I. We multiply, it's equal 6 minus 3i minus 4i plus 2i squared, so it's minus 2 minus 4 plus I. And now simplify 6 and minus 6 to get, so it's equal to minus 6i. Then z is pure imaginary. Z equals 3 minus 4i into 3 plus 4i. This one is in the form complex number times its conjugate. So it's equal to real part squared plus imaginary part squared, which is equal to 25. Z in this case is a real number. Z equal 1 minus I squared is equal to 1 minus 2i minus 1 is identity a squared minus 2ab plus b squared. So it's equal minus 2i, then z is pure imaginary. Z equal 1 plus I power 4, 1 plus I squared into 2, 1 plus I squared, we develop this one, so a squared plus 2ab plus b squared power 2, simplify the 1 and 1, 2i power 2, which is equal 4i squared, and don't forget that I squared equal minus 1, so the final answer is minus 4, then z is a real number. Application 2. Given the two complex numbers z equal x plus iy and z prime equal x prime minus iy prime, where x prime y prime are real numbers, suppose that z prime equal iz plus 2 plus I. So we have a relation between two complex numbers z prime and z. Calculate x prime and y prime in terms of x and y. In this case, we put the relation here. We replace z prime by the algebraic form x prime plus iy prime, and we replace z by x plus iy. X prime plus iy prime we kept. We have to do the calculation here. So ix plus I squared y, which is equal minus y plus 2 plus I. And finally we group here the real part, it's minus y plus 2 plus I into x plus 1. Now, using equality of two complex number, we get x prime, the real part of this complex number in the left member, is equal to the real part of the complex number in the right member. So x prime is equal minus y plus 2 and y prime equal x plus 1. So this is what we get in the slide before. Previous slide. Determine the set of points M of coordinate x, y, the image of z for which z prime is real. Z prime is real, so imaginary of z prime equal to 0. Imaginary of z prime equal to 0. Imaginary of z prime, it's equal to y prime. Y prime equal to 0. Y prime equal to 0, so x plus 1 equal to 0 and x equal minus 1. This one is the equation of a line. So the point M of coordinate xy, verifying this relation x equal minus 1, so M moves on the straight line D of equation x equal minus 1. So if z prime is real, M moves on a straight line of equation x equal minus 1. Determine the set of point mxy as the image of z for which z prime is pure imaginary. If z prime is pure imaginary, real z prime equals 0 and imaginary z prime not equal to 0. We see that before. So x prime equals 0 and y prime not equal to 0. We start by x prime by solving the first equation, x prime equal to 0. So minus y plus 2 equal to 0 and y equal to 2. This is the equation of a line, of a straight line, horizontal line. But in the system we have also y prime not equal to 0. So x plus 1 must be different than 0 and x not equal to minus 1. So then the point M moves on the straight line D of equation y equal to deprived of the point minus 1, 2. So moves on all the line but deprived of the point minus 1, 2. Let me show you that on an activity, GeoGebra activity. here we have the point m prime of affix z prime. M prime is the image of z prime, m is the image of z. Here we have the relation between z prime and z. We have z prime equal iz plus 2 plus I. The first result to verify in the GeoGebra is that if z prime is real, m of affix z moves on the straight line d of equation x equal minus 1. First, before that, if we have a relation between z prime and z, so if m prime change, m change of position, because they have a relation between them. Now, let us verify this result. If z prime is real, so m prime must be on x prime or x, Let me attach the point m prime to x prime or x, and now I will change the position of m prime. When I change the position of m prime, we can check clearly that m moves on the straight line of equation x equal minus 1. Okay, now let me detach the point m prime. Okay, now I want to verify the second result. If z prime is pure imaginary complex number, so m of affix z moves on the straight line d of equation y equal to deprived of the point minus 1, 2. So first, if z prime is a pure imaginary complex number, so m prime must be on y prime or y. So I go and I attach the point m prime on y prime or y. Now let me move m prime to see describe which line. If m prime moves on y prime or y, so if z prime is a pure imaginary number, we can check that very clearly. The point m of affix z moves on the line y equals the horizontal line y equal to deprived of the point minus 1, 2. So you can check that very clearly. Okay, and this is the end. Thank you to see this video.